Thank you very much. Hello, everyone. I'm Dandan working at IST as a research fellow. Today, I will show you some first results that we use the actual observations of intermediate mass strip star to constrain the uncertain process in the binary evolution. Okay. Here we have an evolved star. This binary interaction can strip the thick hydrogen-rich envelope and leaving the hot, compact helium core exposed. This is the strip star I'm going to talk today. And the binary interaction stripping process can be mass transfer or envelope interaction. Both of them are quite uncertain. We have already heard a lot. And especially the mass accretion, angular momentum loss, and envelope ejection. As direct products of binary interaction, strip stars are perfect benchmarks to constrain this process. Actually, strip stars are quite important in a wide variety of astrophysics field. This is the formation channel of double neutron star merger. In this channel, strip stars constitute the two necessary steps here to form strip star. Here, they have the intermediate mass between 2 and 8 solar mass. Given such significance, so many researchers apply different codes to produce lots of intermediate mass hot strip stars in the past half century. This type of star should be common because a large fraction of massive star goes through envelope stripping and they have a long remaining lifetime after stripping. However, observations of these strip stars is not easy. They remain empty until just a couple of years ago. The first group of these stars has been discovered, and then recently we have obtained the first orbital solutions of a subset of these stars. So it's very exciting, and this work is the first time to use these observations to constrain the massive binary evolution. So what you are going to see is in this talk, you will see highly non-conservative okay. In this talk, you will see highly non-conservative mass transfer is expected in this binary system, and the envelope interaction could be followed by additional mass transfer. And during the stable mass transfer, angular momentum loss scheme is less efficient than the expansion according to the traditional treatment of called isotropic remission scheme. Okay, let's start with the data and analyze method. We use observations of strip star in small magnetic clouds, which is from the results of Alex LaRouche, who is a PhD student in University of Toronto. And all of the strip stars are single line spectrum binaries, which means that they have unseen companions here. Mass constraints of these two components are shown in the x-axis and also y-axis. In general, strip stars are much more massive than its companion. We obtained the opto period by solving opto solution, indicated by the color. You can see that star 1 is in a wider opto period than the others. Another important result is the surface hydrogen abundance of the strip star is roughly 0.3 and 0.4. This is weird. We use analytical calculation and MESA models to constrain. Sorry, it doesn't work very well. And MESA models to investigate how the binary interaction help to produce the strip stars. The first question is how much material has been ejected from the system. Here, we show that the binary interaction for the progenitor binary, they are highly non-conservative. And right now, and then we can pick up the several stars to constrain the common envelope interaction. Here, the star 2 and the star 4 shows quite similar properties, short opto period, extreme initial mass ratio. So it tends to develop common envelope interaction. We pick up the star 2 as an example to constrain this process. With expansion during stellar evolution, binding energy of the envelope decreases. So for an initially non-solar mass star, we especially focus on the binding energy just before core helium burning, because it's the least binding energy for the unburned core. And here is the binding energy from the center to the surface. The color in the background shows the hydrogen mass fraction. Here you can see there's a chemical gradient. It works, yes. Chemical gradient between the core and the envelope. We can see that most of the binding energy is located in the chemical gradient. And then where is the boundary for the envelope stripping? In general, boundary is approximated by the location where mass fraction, hydrogen mass fraction equals 0.1. However, we have the strip star, which shows a hydrogen mass fraction 0.3 and 0.4, which indicates that the boundary probably should be its outside. Actually, we found that the binding energy at the outer boundary is 10 times smaller than that in the inner boundary. Okay, right now we can check if the envelope, this part envelope, can be ejected with this lower binding energy. Here you see is the observation of the star 2, the mass and orbital period. We use MESA to simulate a group of stellar models. After applying the alpha formalism, we obtain the final orbital period after common envelope. And the shaded region here takes into account the M2 uncertainty. So it seems that star 2 can be formed from common envelope interaction. However, we find star expands generally during the fast envelope stripping, including the expansion of the boundary. With such expansion, the strip star keep overfilling its Rush lobe with the present observational configuration. To avoid a Rush lobe overfilling, we expect a longer orbital period for this binary after common envelope. But we still want to produce the observed binary with a short orbital period. In this case, we need help of additional mass transfer to shrink the orbital period. That's why we propose the additional mass transfer probably could followed by the interaction the common envelope interactions. Okay, and then we move to the constraints of stable mass transfer. For star 1, orbital period of 300 days is too wide to survive from the common envelope ejection. So we think they should probably come from the stable mass transfer. Angular momentum loss together with ejected material is crucial for the orbital evolution. In general, people think, we assume the material leave the system from the vicinity of the accretor, which is called isotropic re-emission scheme. It is widely used, especially population synthesis code. And here you see the observation of star 1 in the mass and the orbital period plane after applying the isotropic re-emission scheme. You can see that the orbit shrinks too much that we cannot produce the observed orbit of the star 1. And of course, the material can also leave the system from the surrounding of the donor. That is called fast wind scheme, as shown by the orange curve. You can see, okay, the fast wind can produce observed orbit for the star 1, but all of the material leaving the system through the surrounding of the donor, when the material is transferred, go onto the accretor. This is a weird assumption, and we cannot give a physical picture that makes sense. So instead of give picture to tell other people how the material ejected from the system, we try to apply different specific angular momentum laws with the parameter of gamma as shown by the x-axis and the y-axis initial orbital period. It means when the binary mass transfer occurs. The color in the background indicates a final orbital period. To produce the star 1 with 300 days, we can see small specific angular momentum loss is required. Compared to the traditional treatment of angular momentum loss, you can see the orange color is isotropic re-emission scheme, green is fast wind scheme, and the purple region is a gamma, along gamma from our calculation to reproduce the star 1. So isotropic re-emission scheme is too strong to reproduce a strip star 1 in binary. So this is our work is the first time constrain the binary mass transfer using the observations of intermediate mass strip stars, and we showed that highly non-conservative mass transfer is expected in this binary, and common envelope interaction could be followed by additional mass transfer. Angular moment loss during stable mass transfer is less efficient than the traditional treatments called isotropic remission scheme. Okay, thank you. Any comments, questions, welcome.
Dandan. Okay, I think you're in.
Thanks, very nice. So you said at the beginning that you think the short period ones are post-extreme mass ratio because the companions are low mass, I guess. Do you know that the companions are not compact objects?
Sorry, I cannot do it. Can you repeat?
Do you know, I guess for all three of these actually, do you know that the companions are not compact objects?
No, we don't know because an unseen object is unseen object. We can only know that it's the mass constraint.
But if you don't see it, how do you don't know the inclination, right? So it's from, you're assuming an inclination distribution always?
Yes, I think so. I think so. I think Alex do the inclination distribution.
Okay, thanks.
Yes.
Okay, we have Matteo Renzo.
Yeah, this is very nice. I was wondering if there is any hope of including like rotation of the donor, because people doing ballistic calculation of mass leaving from the donor. When the donor is rotating, you can change significantly both the mass transfer efficiency and the torques on the orbit, which is something that is, as far as I know, presently way beyond the capabilities of MESA. But that seems like something that could move a lot your gamma parameter for the angular momentum.
Okay.
Have you ever thought of this?
No, I don't think we have the rotation properties so far, but probably in the future, then I think they will work more. Yes.
Ilya Mandel, thanks for a very nice talk. The first binary you described, I think star 2, why do you assume it's a post-common envelope system? Because the surface helium abundance actually looks a lot like what I would expect from K-say mass transfer. So in just main sequence donor, you get stripped to these intermediate amounts, typically as you recede into what used to be part of the mixing core. And then I think things might actually sort of match the standard models better, because as you say, it's very hard to see why, if it was a common envelope system, why it wouldn't re-expand again with this amount of, if you sort of remove the mass, which is sort of what you're doing, less than a than a surface hydrogen fraction of 0.1.
Okay, so we think the star 2 potentially come from common envelope is because one, it has a short opto period, less than 1 day, and also if we go back to the progenitor binary, it has extremely mass ratio smaller than 0.1. In that case, it tends to develop common envelope interaction.
But that's an assumption based on, you're assuming that it's a common envelope system to say what the mass ratio was initially.
Yes. Yes, it's true. We based on the strip star mass and go back to how much mass initially it has. Yes, and but we agree that if the progenitor with extreme mass ratio is tend to start a common envelope interaction, right? In that case, I think the only uncertainty here is if the initial mass with the strip mass is a good couple, a good relation here. It can be some difference with the overshooting uncertainties.
Adam Barrows.
Thank you. Very stimulating talk. I don't follow the subject very closely, so could you clarify how what you're talking about concerning non-conservative mass transfer is not inconsistent or consistent with the previous speaker's talk?
Okay. The main huge difference is we think these strip stars we show here, they are highly non-conservative mass transfer. Tipo, he showed that group of strip star is highly conservative mass transfer.
So these aren't inconsistent?
This is non-consistent.
Okay.
Yes, I can show you.
So they are not consistent?
Yes, yes, these are non-consistent.
Okay, very quickly, a follow on. I don't follow this subject either, but Andre Pecha has talked about non-conservative transfer through ejection of matter through L2. And when you're talking about these types of transfers, why aren't we talking about that as well? What is the special case that he's looking at that is not relevant to what you're looking at?
Okay, if you're talking about outflow from L2,
Yeah.
and it will be also quite intense binary interaction. It's in the
Okay, so it's an extreme situation.
I think it is, yeah, I think so. And also, right now we haven't have a very detailed binary simulation, especially for the extremely mass binary with extreme mass ratio. If we simulate the binary extreme mass ratio, it is possible that some of them may have this L2 outflow.
Thank you.
Yes. Okay.
Let's thank Dandan again, and